This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, we are going to discuss about question bank questions related to feedback amplifiers. So before going to discuss the questions related to fourth module, that is feedback amplifier, just we will revise what are the contents we learned in the case of feedback amplifiers. So here, in the case of feedback amplifiers, we have learned what is meant by feedback, the concept of the feedback, and why we are moving for the concept of feedback in the case of amplifiers, and what are the different classifications of the feedback, and what are the different types of feedback amplifiers, and the characteristics of the negative feedback amplifier, and the effect of feedback and amplifier characteristics. So, and we are going to analyze the four types of feedback amplifiers. Those are voltage series, voltage shunt, current series, and current shunt feedback configurations. And next part of this one is the oscillator. So in the case of oscillator, we are going to see the condition to design the oscillators and the different types of oscillators. In that, we are having RC type of oscillators and LC type of oscillators. In the case of RC type, we are having RC phase shift as well as Wien bridge oscillators. And in the case of LC type oscillators, we are having Hartley oscillator as well as colpitts oscillators. So now we are going to discuss the questions related to these feedback amplifiers as well as oscillator circuits. So here we are having three types of questions. Part A belongs to the problem solving and critical thinking questions, and part B is long answer questions, and part C is short answer questions. So we'll move into the problem solving and critical thinking questions. In that, first question related to the problem, related to the feedback amplifier. So here they given the feedback amplifier parameters, that is the voltage gain AV equal to minus 100, and the input voltage to the system is V1 equal to 1 millivolt. And here we need to find the closed loop voltage amplification, that is closed loop voltage amplification as well as output feedback voltage, that is VF, and the input voltage to the amplifier, and what is the input voltage we are providing for the amplifier, and the type of feedback for A beta equal to 0.01 and B beta equal to minus 0.005 here, and beta equal to 0 and beta equal to 0.01. And also we need to determine the percentage variation in the voltage gain resulting from 100% increase in A. So, and also when beta equal to 0.01, when voltage gain equal to minus 100 and AB dash equal to minus 50, in that case we have to find how much percentage variation in the gain. So these are the parameters we need to calculate from this particular problem. So this problem we already discussed in the case of problems on feedback amplifiers, and just we are having the formulas for this. Substitute the given values in that so that we can able to find the desired parameters. And next one is, an amplifier has a midband gain of 125. So gain given it as 125 here, and a bandwidth of 250 kilohertz. And if 4% negative feedback is introduced, so feedback is 4% is introduced, find the new bandwidth gain. Okay, what is the new bandwidth and what is the new gain in this case? So the given voltage gain as well as bandwidth value, and after producing the 4% negative feedback to the amplifier, what is the new bandwidth and what is the new gain, we need to calculate it. So this problem also we already discussed in the case of problems on feedback amplifiers session. And next, an amplifier with open loop voltage gain AV equal to 1000 plus or minus 100 is available. It is necessary to have an amplifier where voltage gain varies by not more than plus or minus 0.1% here. So here we need to find the reverse transmission factor, that is beta, as well as the gain with feedback, that is AVF. So here to find the beta value, we are having VF by V0 here. And to find the AVF voltage, we are having AV by 1 plus AV beta. So once we find the beta value, we can also find the gain with feedback. So this problem also we already discussed in the problems on feedback amplifier session. And next, we're coming to the next problem. An amplifier with voltage gain of minus 500 produces 5% harmonic distortion. So the distortion value is 5% at full output. Illustrate the value of beta to reduce the distortion to 0.1% here. And also find the overall voltage gain. So this is also similar to the previous kind of problem only. First find the beta value, then find the voltage gain by utilizing AV by 1 plus AV beta formula. So this problem also we already discussed in the problems on feedback amplifier session. And next problem is for a voltage series feedback amplifier, find the distortion, gain with feedback, input impedance as well as output impedance here. So this is the circuit given in the problem itself. So in this particular kind of problem, first of all, we have to identify the topology. And also find the input side and output side circuits. Find input and output parameters or circuit side parameters. Okay, then go with the analysis of the given circuit after converting into H parameter model. Then find the asked parameters, that is the fourth step, that is distortion is how much, gain is how much, input impedance is how much, and the output impedance is how much. So this problem also we discussed in the problems on feedback amplifier session. And next problem related to the oscillators here. Why? Because they given it as Hartley oscillator. Is designed with the inductance 20 microhenries and a variable capacitance. Find the range of capacitance values if the frequency of oscillation is varied between 950 kHz to 2050 kHz. That is nothing but wherever the minimum frequency is 950 kHz and the maximum frequency is 2050 kHz. So we need to find the capacitance value at F minimum as well as at F maximum by utilizing the frequency of oscillation formula of the Hartley oscillator. So this problem we already discussed in the problems on oscillators session. And next one is again question belongs to the oscillators, that is Hartley oscillator. It is utilizing two inductances, that is L1 equal to 2 millihenries and L2 equal to 20 megahenries, while the frequency is to be changed from, that is F minimum is 950 kHz and the F maximum value is 2050 kHz. Calculate the range over which the capacitors are required here. This problem is also similar to the previous problem and we have already discussed in the problems on oscillators session. And next problem belongs to the crystal oscillator here. So in the case of a crystal oscillator, we are going to utilize the resistor, capacitor and inductor components. So that's why in the problem they given it as inductance value 2 henries, capacitance value as 0.01 picofarads and the resistance value as 2 kiloohms. And the mounting capacitance Cm is given it as 2 picofarads. So here we need to find the parallel resonant frequency of this crystal oscillator by utilizing the formula of the parallel resonant frequency. So this problem we already discussed in the problems on oscillator session. And next problem also related to the quartz crystal oscillator here. So the given parameters are L equal to 50 millihenries and C1 equal to 0.02 picofarads and the resistance equal to 500 ohms and the C2 value is given it as 12 picofarads. So here we need to find the series resonant frequency as well as parallel resonant frequency of the given crystal oscillator. So this problem also we already discussed in the problems on oscillators session. And next problem belongs to the power amplifier. So here we need to calculate resistor. So what are the necessary reasonable data required here? We have to consider to find the parameters of this power amplifier. And next part is the Lang answer questions. In the part B, first question is explain the concept of feedback as applied to electronic circuits. So generally this feedback concept we are introducing in the amplifier circuits in order to improve their amplifier parameters. So the feedback is nothing but we are taking some part of the output and again giving back to the input of the amplifier. So if any amplifier utilizing this concept, that amplifier we are calling it as the feedback amplifier. So advantages of this feedback amplifier, it will reduce the noise as well as it will provide the stable amplification across the output. So here we are having two types of feedback, positive feedback as well as negative feedback. So this is the amplifier circuit. So the output of this amplifier circuit we are again giving back to the input of the amplifier through this feedback network, where beta is nothing but the feedback ratio. Suppose if you are giving the input as voltage and the output also we will get it as voltage, and this output voltage we are giving to the input of the feedback network and the output we will get it as the feedback voltage. So this feedback ratio value is Vf by V0 here. And after including the feedback to the amplifier, this becomes the feedback amplifier. While performing the feedback amplification, we are going to do the sampling across the output side and mixing across the input side. Sampling in order to take the some part of the output signal, and mixing here we are adding the feedback signal with the input signal. So here gain without feedback is output voltage by input voltage. If we calculate the gain with feedback is, that is output voltage by source voltage Vs here. And this sampling is different for voltage and current. If you are going for the voltage sampling, then it is the shunt circuit, and we are going for the shunt sampling. And if it is the current sampling, we are going to connect the series circuit. Similarly, across the mixing, we are going to add or subtract the feedback signal to the input signal. So this is also different for voltage and current. If you are using the voltage signal, we need to go for the series mixing. If you are going for the current mixing, we need to go for the shunt mixing. So next one is illustrate the advantages and disadvantages of positive and negative feedback. So here we are going to explain in detail about all the advantages and disadvantages of positive and negative feedback here. So basic advantage the positive feedback is it will generate the oscillations, and the disadvantages is it leads instability in the circuit and it will reduces the bandwidth and improves the distortion and also the noise. So while coming to the advantages of the negative feedback, it will stabilize the gain, reduce the noise and distortion, and it will improve the input impedance and reduce the output impedance. The only disadvantage of negative feedback is reduction in gain. So these parameters we have to prove mathematically as it is the Lang answer question. Next one is with the help of general block schematic diagram, explain the term feedback here. So the same feedback amplifier whatever we used in the previous slide, I have considered here. So here each and every block of this particular schematic diagram we need to explain in detail, and also we need to calculate the open loop gain as well as closed loop gain of the amplifier here. And next up, illustrate types of feedback is used in electronic amplifiers and illustrate the advantage of this type of feedback. Prove each one is mathematically. So here we have two types of feedbacks, that is the positive feedback and negative feedback. So whenever the feedback energy is in phase with the input signal, so that it is called as the positive feedback. So in the case of positive feedback, we are having the amplifier and feedback network. So the feedback signal is adding with the input signal here. So generally the amplifier circuit will introduce the 180 degrees phase shift, and the feedback circuit we have to design in such a way that it should also introduce 180 degrees phase shift here. So the overall phase shift provided by the circuit is 360 degrees or 0 degrees. So that's why the input signal as well as feedback signal are in phase with phase in the case of positive feedback circuit. And to design the amplifier, we can utilize either BJT or field effect transistor here, and it will introduce the 180 degrees phase shift. Suppose if we take it as the common emitter configuration. So each and every step we have to explain detail as it is the long question. And the gain calculation, the input signal we are taking, the gain is the V0 by Vs signal with feedback we are calculating. So the value of Vs I am substituting, that is the difference of the input voltage and the feedback signal. So after simplification, it is A by 1 minus A beta. So AF is the gain with feedback, A is the gain without feedback, and A beta is the loop gain here. And these are the advantages of the positive feedback as well as disadvantages of the positive feedback. And next, coming to the negative feedback. So negative feedback circuit, in this case, we are subtracting the input signal from the feedback signal, and the output signal is 180 degrees phase shift with the input signal in the case of negative feedback. That is the difference between the positive and negative feedback. So in this case also, we need to explain each and every block in detail, and we need to mention, we need to calculate the gain. We will get it as A by 1 plus A beta, and we need to mention all advantages and disadvantages of this particular positive and negative feedbacks. And next one is explain with the relevant information how the negative feedback improves stability, reduce noise, and increase input impedance. So in order to prove this, I am taking the gain with feedback, and to prove that distortion is reducing, I am differentiating this one with respect to A here. So the variation of DAF with respect to DA we are doing here. So we are getting this much value. So here the fractional change in amplification feedback divided by the fractional change in feedback without feedback is called as the transfer gain here. So the reciprocal of this sensitivity will give the desensitivity here. So the value of that one is B equal to 1 plus A beta. So the desensitivity value is very high in the case of negative feedback. And so here the noise factor is also reduced by 1 by 1 plus A beta times in the case of introducing the feedback in the amplifier circuit. And also the input impedance is increasing 1 plus A beta times in the case of introducing the negative feedback. So each and every step we need to explain clearly as it is the long observation. Next, give the equivalent circuits and characteristics of ideal and practical amplifiers of the following types, that is the voltage amplifier, current amplifier, trans resistance, and transconductance. So here we know that voltage amplifier is nothing but the input is voltage as well as output is also voltage here in the case of voltage amplifier, and that's why it is called as the voltage amplifier. And while coming to the current amplifier, it provides the output current corresponding to the applied input current here. So that's why it is the current amplifier. It will amplify the current signal. And the transconductance amplifier. So conductance amplifier means in this case the output current is proportional to the signal voltage. So the output is the current, input is the voltage here. So the parameters are different across the input side and output side. So that's why we are indicating with the trans here. And similarly trans resistance amplifier. So in this case, it will provide the corresponding output voltage for the applied input current here. So that is the trans resistance amplifier. So this is the equivalent circuit of the voltage amplifier. To draw the equivalent circuit of voltage amplifier, input side as well as the output side, we have to utilize the Thevenin's theorem. And similarly, to draw the current amplifier, we have to utilize Norton's equivalent circuit across the input side as well as the output side. And this is the transconductance amplifier. Here across the input side, we have to use the Thevenin's equivalent circuit. Across the output side, we have to utilize the Norton's equivalent circuit. In the trans resistance amplifier, across the input side, we have to utilize the Norton's equivalent circuit. Across the output side, we have to utilize the Thevenin's equivalent circuit. So these are the equivalent circuits of the types of all the amplifiers. We have to explain each and every amplifier clearly, and what is the effect of input and output impedances we need to explain clearly here. And next, derive the expression for the input resistance with feedback and output resistance with feedback. In the case of voltage series amplifier as well as voltage in all the feedback amplifiers, we have to find the input and output impedances. So here we have to take all the topologies networks and we have to take the formulas of all the topology feedback networks, then find the input output resistance values. And next, in which type of amplifier the input impedance increases and the output impedance decreases with the negative impedance. Prove the same drawing equivalent circuit here. So generally, if you use a negative feedback, if we introduce a negative feedback to the amplifier circuit, the input impedance will improve and the output impedance will be decreases here. So we can draw that particular equivalent circuits here, and we have to prove by utilizing the mathematical equations here. And next, draw the circuit of voltage series feedback amplifier and justify the type of feedback. So here once we can call it as the voltage series means we are doing voltage sampling and series mixing. So we can also call it as series shunt amplifier. So in this case, the output as well as input both are the input signals only. So it is the voltage amplifier. Okay. So here amplifier input is Vin. So the output is V0. So that signal we are applying here, we are getting the VF feedback signal. So this is the H parameter equivalent circuit of the voltage series amplifier. So we have to analyze this particular circuit in order to justify the type of feedback. Next, derive the expressions for the voltage gain, input impedance, output impedance for the current series feedback amplifier circuit. So this is the circuit of the current series feedback amplifier. So here output is taken as a feedback and the output current is connected in series with the input circuit here. So this is the input voltage is proportional to the output current. So it is the transconductance amplifier here. And next, so here we need to derive the voltage gain as well as input impedance, output impedance from this particular circuit. For that purpose, we have to draw the H parameter equivalent circuit of the amplifier, and then we need to find all the parameters. And next, explain the basic principle of generation of oscillations in LC tank circuits. So this is the general diagram applicable for the colpitts oscillator as well as Hartley oscillator. So here we are using the amplifier, and this combination of three impedances will give the feedback network here. So from this feedback network and amplifier, we need to find the frequency of oscillations here. Okay. So we need to explain about the amplifier clearly and feedback network clearly, and we have to replace the amplifier with its equivalent H parameter model. And these impedances, we are writing it as the equivalent impedance. Okay, and this equivalent impedance we are taking it as the load impedance, and after substituting all the values, we are getting the load impedance. So to find the gain of this one, we are taking the total circuit. Okay, and we are applying the voltage division rule to find the VF. And finally, we are calculating the beta value, that is feedback ratio. So after finding the feedback ratio, we have to do AV into beta to find the frequency of oscillations as well as gain value. So that's why we are taking AV beta is greater than 1. So we have to substitute the A value as well as beta value here. So A value this one and the beta value, we need to substitute that both and we have to simplify it. So this is the general equation for the LC oscillators. So this we can utilize for the Hartley oscillator as well as the colpitts oscillators in order to find the frequency of oscillation as well as the gain equation. And next, illustrate the Barkasian criteria for the generation of sustained oscillations. So generally, if we want to design any oscillator circuit, we have to satisfy two conditions. That is, the open loop gain of the amplifier must be 1, and the phase angle provided by the amplifier is either 0 degrees or 360 degrees. So to design any oscillator circuit, we have to satisfy the two conditions here. So we need to explain each and every step clearly here again. And next, how are the oscillations initiated here? So generally, the oscillator starts generating oscillations by amplifying the noise voltage which is always present. So this noise voltage is a result of the movement of free electrons under the influence of room temperature. So this noise voltage is not exactly in sinusoidal due to saturation conditions of practical circuit here. So the noise signal will be sinusoidal when A beta value is close to 1. So in practice, this value is greater than 1. So later the circuit itself adjusts the modulus of AB equal to 1 and with a phase shift of 360 degrees here. In this way, the oscillations are initiated in the circuit and we have to explain in detail as it is the Langens. And next, draw the circuit and explain the principle of operation of RC phase shift oscillator. So RC phase shift oscillator belongs to the RC type of oscillators. So this is the amplifier circuit here and this is the feedback network. Okay, to provide the 180 degrees phase shift, and it uses the positive feedback which provides 360 degrees phase angle. So we need to take the equivalent circuit of this one and we have to explain the operation of this one in detail and we have to find the frequency of oscillation of this one and it will generate the sinusoidal signals and it can generate the frequencies up to 20 kilohertz only. So that's why it's a low frequency oscillator. So this is the equivalent circuit. And next, illustrate the expression for the frequency of Hartley oscillator. So in the case of Hartley oscillator, in the feedback network, we are going to utilize 2 inductors and 1 capacitor. The amplifier is as it is in all the oscillator circuits. So in the previous slides, we have already derived the general expression for the LC oscillator. By utilizing the general expression, we can able to find the equation of the LC oscillator here. So it resonant frequency imaginary terms should be 0. After making the imaginary terms to 0 and after simplification, the frequency of this oscillator is this much, 1 by 2 pi under root of L1 plus L2 into plus 2m into C here. And the gain value is this much for the Hartley oscillator. Next, derive the expression for the frequency of colpitts oscillator. So in the case of colpitts oscillator, in the feedback network, we are going to utilize 2 capacitors and 1 inductor and the amplifier is C. Again, to find the frequency, first of all, we have to explain the operation of this one, each and every element, how they are working, and we have to take the equivalent circuit of this one. Then we have to go for the analysis. So while going for the analysis, we have to take the general equation of the LC oscillator, and in the impedances, we have to substitute these values. So after substituting the values, we are getting this much value. So to find the frequency of oscillation, we have to take the imaginary terms must be 0. After making the imaginary terms 0 and after simplification, so the frequency of oscillation, we will get it as this much, 1 by 2 pi under root of L into C equivalent. And next, what is the condition for oscillation? Here it is. That is F equal to C2 by C1. We need to maintain to get the sustained oscillations in the given oscillator. So we need to derive the expressions clearly and we need to explain the operation and construction clearly here. And next, derive the expression for the frequency of Wien bridge oscillator. So in the Wien bridge oscillator, we are going to utilize the 2 stages of the amplifier and 1 feedback network in the form of bridge. So we have to analyze this circuit to find the frequency of oscillations. Okay, we are taking the impedances from the circuit. We are calculating the overall impedance and the feedback ratio value. And after that, we have to substitute that impedances to find the beta value feedback ratio. And after that, we need to find the gain and the feedback ratio value. And after that, at frequency of oscillation, imaginary terms must be 0. After making the imaginary terms 0, we have to find the frequency. That value is 1 by 2 by RC here. And next condition for the oscillator is according to Babitha criteria. These values, it must be satisfied here. So each and every step as well as analysis, we have to explain clearly as it is the Langens equation. And next, derive the expression for the frequency of crystal oscillators. In the case of crystal oscillators, we are going to utilize the resistors, capacitors as well as inductors to generate the sustained oscillations here. So here we are having series resonant frequency. F is equal to 1 by 2 pi root Ls into Cs from the circuit we can calculate, as well as parallel resonant frequency we have to calculate here. So we have to draw the circuit and clearly explain the operation and find the series as well as parallel resonant frequencies from the crystal oscillator. And next, explain how better frequency stability is obtained in crystal oscillator. So because of using swamping capacitors and regulating the power supply circuit, we can able to stabilize this circuit. And again here also we need to explain the total operation of the crystal oscillator here. And next, draw the equivalent circuit for a crystal and explain how oscillations can be generated in electronic circuits using crystals. So this is the equivalent circuit of the crystal here. So we need to explain in detail about this crystal oscillator again here. And while coming to the next part, that is the shunt answer questions. So first one is define feedback and illustrate the types of feedback amplifiers. So here the phenomenon of adding some portion of the output signal to the input of the amplifier will give the feedback. Here we are having 4 types of feedback amplifiers, that is voltage series, voltage shunt, current series and current shunt feedback amplifiers. And next, demonstrate the positive and negative feedback. So positive feedback, in the positive feedback we will add the input signal to the feedback signal, but in the case of negative feedback we will subtract the input signal and the feedback signal here. But negative signal will provide the more stability compared to the positive feedback. List advantages and disadvantages of negative feedback. So these are the different advantages of the negative feedback. It stabilizes the gain and reduce the noise and distortion, and improves the bandwidth and input resistance, and reduce the output resistance. So these are the basic advantages of the negative feedback. And while coming to the disadvantage, it will reduce the gain. That is the drawback of the negative feedback. And next, compare voltage and current feedback sampling in amplifiers. So here, if the signal is voltage, the sampling is different. If the signal is current, sampling is different. If it is the voltage sampling, always we have to do the shunt connection. If it is the current sampling, always we have to do the series connection here. That we have to explain clearly here. And next, define sensitivity. Sensitivity is nothing but the fractional change in amplification with feedback divided by the fractional change in amplification without feedback. That is nothing but DAF by DA will give the sensitivity here. Desensitivity means the reciprocal of the sensitivity will give the desensitivity here. So the desensitivity factor will be more in the case of negative feedback compared to the positive feedback. And next, define feedback factor or feedback ratio. So generally we will represent it with beta. So this one is nothing but the ratio of feedback signal to the output signal, that may be the voltage or current here. And outline the advantage of introducing negative feedback. So negative feedback will reduce the noise and distortion, and improves the bandwidth range of the amplifier, and improves the input impedance and reduce the output impedance, and it will provide the distortionless output across the amplifier. And next, to define the loop gain or return ratio. So generally loop gain or return ratio we will indicate with A beta value. So a path of signal from input terminals through basic amplifier through the feedback network and back to the input terminals forms a loop. So the gain of that particular loop is the product of A beta here. Illustrate is the effect of lower cutoff frequency with the negative feedback. So what is the effect of lower cutoff frequency? Here it is. So the cutoff frequencies for a negative feedback amplifier designed for a closed loop gain of 100 would occur when the open loop gain falls to 100 again. So it is seen that the negative feedback increases the amplifier bandwidth. That is nothing but the amplifier bandwidth is essentially equal to the upper cutoff frequency of the amplifier. Next one is, what is an oscillator circuit? So oscillator is an electronic circuit which can be used to generate the different types of waveforms without applying any input signal. If we provide the DC signal to the oscillator, it will generate the oscillations. And next, list the classifications of oscillators. So these are the different types of oscillators: RC oscillator, Weinbridge oscillator, Hartley oscillator, Colpitts oscillator, crystal oscillator, Armstrong oscillators, etc. So here in all the cases, the amplifier is similar. The only feedback network is differentiated by utilizing the different types of resistors, capacitors and inductors, utilization of the designing of feedback network. And next, interpret the types of feedback oscillators. So here we are having 3 types of feedback oscillators, that is the RC oscillator, LC oscillator and crystal oscillator. And next, define electric effect. It is the ability of a certain material to generate an electric charge in response to applied mechanism stress, that is T here. Next, draw the equivalent circuit of a crystal here. So this is the crystal and this is the equivalent circuit of the crystal that consists of the resistance, inductance as well as series and parallel capacitances. Illustrate is Miller crystal oscillator. Explain its operation. So Miller crystal oscillator, we have to explain that, and what is its operation we need to explain clearly here. And what is the frequency for RC phase shift oscillator? So frequency of RC phase shift oscillator is if R of 10 kilo ohms and the capacitance of 0.01 microfarads in each of its 3 RC sections. So the overall one is the frequency of the RC phase shift oscillator. And it give the topology of current amplifier with current shunts. So this is the current amplifier with current shunt circuit here. Next, calculate the frequency of oscillation, that is F0 for the clap oscillator with C1 equal to 0.1 microfarad, C2 equal to 1 microfarad, C3 equal to 100 picofarads, and the inductance equal to 470 microhenries here. So this is the given values. From this we need to find the frequency of oscillation of the clap oscillator. So this problem we already discussed in the problems and oscillators session. And next, illustrate the conditions for the sustained oscillator or illustrate the Barkasian criteria. So according to the Barkasian criteria, the open loop gain must be greater than or equal to 1 and the loop gain phase angle must be 0 degrees or 360 degrees. Then only we will get the sustained oscillations without over damping or under damping here. So in this session, we have discussed the questions related to the feedback amplifiers as well as oscillators. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.